Hello and welcome to, this will be the fourth and final video for week 5. It's going to end up giving us a little over 3 hours total of videos, I think. So getting a little bit more, and I think this video will get me caught up to where I actually want to be, and it's already Sunday of week 5, so I think I'm finally where I want us to be in terms of having these videos published. So what are we going to do in this video? We're going to look at system calls, specifically sysread and syswrite. You already saw an example in that first program that we wrote 3 weeks ago now. We saw an example of syswrite there, but we're going to learn in a little bit more detail what a system call is, and a little bit more concretely how you set up these system calls for reading and writing. And so we're basically going to get into it in a hands-on sense. But I do want you to call your attention to these notes here. And before we do that, let me just call your attention to the updated readings tab. And I did send an email out about this, but I just wanted to let you know that if you haven't been reading the textbook, you're probably fine, but you do want to start reading it. I've been taking a different approach than the textbook, so think of the textbook as a supplemental way of learning this more or less the same material. It's going to fill in holes, maybe where I didn't specifically mention something, take a different approach to teaching some of the same things. But I do want you to be aware of some important differences in what I've been doing in these videos versus what you see in the textbook. In particular, the textbook launches right into using the GCC compiler to do the linking step. Something you may not have realized about GCC previously was that GCC actually calls LD. We use LD here to do the linking. GCC would compile a C program. Actually, GCC might actually use an assembler. It doesn't use NASM, but it will use an assembler. I believe it's called GAS, G-A-S, for the GNU assembler, A-S for assembler, and G for GNU. GCC is the GNU C compiler, if you didn't know what the G was in there. So GCC actually, behind the scenes, generates assembly code, gives it to the GAS assembler, the GAS assembler. The GAS assembler produces a .o file. That .o file is handed off to LD, but GCC manages all that behind the scenes for us, calling those things for us. And that's what the author of the book chose to do, is just kind of launch right into using GCC as the linker, in part because he also provides this ASMIO library object file that has a number of useful functions for doing input and output in a somewhat more straightforward way than what we are going to do. What we're going to do is work with raw assembly language and work directly with system calls. So I don't want you, until I tell you otherwise, I don't want you to use GCC to link your programs. I don't want you to use this ASMIO.o library. You can get this off of his website that we link to for the textbook. So, I mean, if you read his textbook, follow his examples, follow his instructions and additional instructions he provides on the website, that's fine. If you want to work with his examples and use GCC for that, but for the problems I give you and for the examples I want us to do in the videos I'm creating, we're not using GCC and we're not using his library. We will actually probably end up building our own library. Sort of, it probably won't have as many functions as he provides here, but we're going to kind of build up our own library. So we'll be learning about libraries, linking libraries, what that actually means, rather than having that handed to you. So you're actually going to kind of learn how to build up something like this ASMIO library for yourself. So I just wanted you to be aware of those differences between what I'm doing in these videos and what is in the textbook. So, because if you go into the textbook and you see he says use GCC, and he's got all these print functions that he can call, well, that's because he's kind of doing that stuff for you, whereas I want you to learn to do some of that stuff for yourself. So just wanted you to be aware of that difference. It would be good, though, to go ahead and read the book up to about chapter 2 at this point. Maybe by the end of this week and middle of next week, sometime in that ballpark, try to read the entire book through entire chapter 1 and not the entire book, the entire chapter 1 and the entire chapter 2 from the textbook. But do keep in mind that he is taking this different approach. But it would be worthwhile to follow his examples, and you have the tools. If you have Linux set up, then you have GCC. You can download his library files, build those, and so forth, and so you should be able to build and run his examples. Just keep in mind that we're doing something a little bit different in the videos that I'm presenting. All right, so coming back over here, so we're going to look at system calls. System call is how in our first program we were able to print a message, and I don't know that I want to go in detail through these notes in the video. You can read these on your own. I may come back and point some things out here as I'm working through examples, but just a quick overview. What is a system call? A system call is basically a way for a program to ask the operating system to perform certain services. And what kind of services would those be? Well, almost anything that a computer can physically do. Most of the interesting things a computer can do nowadays are kind of the operating system sort of serves as a gatekeeper to all the hardware capabilities of a typical computer. So even things as simple as getting input from the keyboard that's being typed in by the user, ultimately you have to, any program that wants to get input from the user ultimately has to ask the operating system to do that. So, and what's the difference between a system call and things you've already learned about, like library calls, like scanf in C programming or some of the other input commands? Well, scanf behind the scenes ultimately is doing system calls. Scanf is not a system call. Getc, if you've used that one, that's not a system call either. But both of those ultimately use a system call to get their job done. They would ultimately do a sysread, which is what we're going to be learning about now. Similarly, printf ultimately behind the scenes is going to be doing a syswrite, which is something we're going to be learning about as well. In fact, you've already seen the syswrite in that first example program. So I just want you to kind of be aware of that. And the other thing is that system calls are invoked in the i386 architecture. System calls are invoked by what we call an interrupt. And why don't I zoom this a little bit since it's on video so you can see what I'm talking about here. So yeah, so system calls are invoked by what we call an interrupt, and I'm not going to go through all these notes I put down here on the interrupt, but you should read through these. Hopefully you find this kind of outline bullet arrangement of information useful. I think this is probably more useful than paragraphs of text. You can quickly get to the information. You can see how it's organized, what's related to what. Gives it a nice hierarchical structure. But you should actually read all of this. Consider the notes. Certainly consider the notes in the class part of required reading. So you should read all of this to make sure you understand what interrupts are, what we're actually doing with the interrupts, and so forth. But the basic aspect of an interrupt is an interrupt causes the CPU to drop what it's doing, i.e. the program that it's running and the instruction that it's about to perform right at that moment, stops doing that, jumps to do some other instructions that are part of what's called the operating system kernel, and it follows those instructions to do whatever the system call was. Well, I should say, in an interrupt, it's going to do whatever instructions are appropriate for the particular interrupt it gets. The kind of interrupt we're using is specifically an interrupt that generates system calls. That's what that hex 80, all right, That's actually a hex 128, but it's a hex 80. Or I'm sorry, that's actually a decimal 128, but it's a hex 80. 8 times 16 is 128. So an interrupt, specifically this type of interrupt, is what causes a system call. And that's what we will be using here. So beyond that, I may come back and talk about what we have here in the notes here, but you should definitely read this. Maybe do some Googling about interrupts on 386 CPUs and in Linux and system calls. Get some additional information on your own. And also see what the textbook has to say about it, if anything. Actually, I don't recall since the textbook provides you with a library of I/O routines, I'm not sure it goes into depth on the system calls at the moment. But at any rate, that's what we're going to do right now. So let's pop over to the virtual machine and start a new program. So here we are, and I've already done a new file here, and I'm going to do a quick file save as, and we'll call this, I'm going to call this read and reverse.asm. So previously we took some data in buffers and arrays in memory and reverse them to other buffers, but here we're going to actually read some stuff in and reverse. So the idea here is read in lines of text from standard input, which normally means input from the user, but we're going to learn about how that's not always the case. But normally that means input typed by the user. So I should maybe be specific there. Print each line in reverse. And to make this a little bit simpler, we will assume that each line is never longer than, let's say 1,000 characters. Sounds good. Actually, for now, I'm going to make that smaller. Let's just so we can do some examples where we have lines that are longer than that. Let's say we'll assume each line is no longer than 40 characters, or 80 is a fairly standard line length. That's what we'll set. We'll assume each line is no longer than 80 characters. Later we can bump that up to 1,000 or something. But I want to make it easy to go over the line size, just so we can deal with that situation. So at any rate, let's do a section.txt here, and we need to define our global symbol start. That's just so the linker knows about the start symbol, which it needs because that tells the linker where the first instruction of the program is. And so this is all kind of standard stuff. And it seems like it's a quirk of gedit. It's not doing the syntax coloring there. I think I have to close this file and open it again. Wonder if reopen close tab will do it. Yep, that's enough to do it. All right, now I'm getting the syntax coloring. For some reason, if you do the save as first before there's anything in there, it doesn't figure out how to color things. So now we have syntax highlighted. All right, so here we go. What do we need to do here? Well, actually, I want to think about first my data or my BSS section. And actually, I'm going to use the BSS section because I don't really need initialized data here, because I'm going to read the data that's going to go into my buffer that I'm going to create. So I'm just going to call this input buffer, and this is going to be bytes of data, so I'm going to use the db keyword, and I just have to decide how many. Well, for that, we'll use 80. However, just to make things a little more interesting, instead of putting 80 here, let's create a symbol called buffer size and use the EQU symbol and just say that the buffer size is 80. Okay? And then here and here, I will use buffer size there instead of the 80. That's just, again, you use this EQU to usually define numerical constants, such as this, just so you can use those kind of like variables. But remember, this is all determined at assembly time. The assembler knows what the value of this is, and it just uses the 80 to determine how many bytes it's going to reserve here with this dB. Oops, I don't want a dB there. This is in the BS. I want uninitialized data, so I want a resb of a particular size buffer. So this says reserve 80 bytes, okay? And input buffer, that's just defined to be the address of the first byte of that buffer. And I'm also going to want an output buffer. And just to make those a little shorter, I think I'm going to go in buffer and out buffer. How's that sound? And let's do resb there, also of buffer size. And the idea here is I'm going to read in characters, a line of characters from standard input, store it in the input buffer, and then I'm going to reverse it to the output buffer and print it out. There is one quirk there, which is you always want the new line at the end, so we don't want to reverse the new line character, which will be one of the characters read in. So let's just keep that in mind as we're going here. All right, so first let's just figure out how to read one line and print that line back out. So that's all I'm going to do right now. Read in one line of text up to buffer size max characters. Okay, so we can't read a line if our buffer is only 80 characters. We don't want to try to read a longer line than that. So what we have to do is set up a sysread. So that's what we're going to do in the next few commands. Now let me show you a nice resource online that can help. Whoops. I don't want all this. There we go. And this website here, I have put in our notes as a resource.